My name is Martin. I have my own company called Coffee Cup Consulting. I'm also one of the guys who organizes the events of the Bulgarian Java user group along with a few other guys. I'm also a big OpenJDK and Oracle database enthusiast, and if you want, you can follow me on Twitter. I tweet about events, technology, and stuff like this. I also have a book called Learning RabbitMQ. If anyone is interested in messaging, you can find me after the session and we can discuss this topic as well. So, in this talk, first we'll provide an overview of what is the Graal virtual machine about. Then we'll show some examples of how to build and basically manage the Graal virtual machine using the utilities provided by the Graal team. Then we'll see some performance benchmarks on how does the Graal virtual machine position compared to the current Hotspot virtual machine. And finally, we'll conclude the session with a few future discussions for the development of the Graal virtual machine. So, the Graal virtual machine. Just before we dive into the topic of Graal, let's have some background information. How many of you know what's the difference between static and dynamic compilation? A few people? Okay, so then to give you some more background, static compilation, as you probably guess, this is the process of compilating your source code, and basically this is right before running your application. When you compile your source code, you can execute it in a compiled form from the runtime. However, on the other hand, the process of dynamic compilation is when basically you have some form or intermediate form of source code and you want to execute it in the runtime and possibly compile it dynamically. And basically the Java virtual machine, as probably most of you know, combines static and dynamic compilation. Statically we combine Java source code to intermediate bytecode, and at runtime, if the JVM decides that it can optimize this bytecode to machine code, it compiles it. However, it can also de-optimize this runtime compiled code. In case, for example, the virtual machine decides that this compiled code is not very optimal, it can de-optimize it back to bytecode. So this is basically the difference between static and dynamic compilation. And the JVM performs this quite well. It introduces a lot of performance improvements over this process, and it has been introduced over the years. And in that regard, Graal essentially is a new just-in-time compiler for the virtual machine. So it basically strives to bring the performance of Java to dynamic languages that run into the Java virtual machine. For example, imagine that you need a JavaScript or a Ruby interpreter that runs in the JVM. If you write your own, basically you won't be so sure that its performance will be as good as the one that you would like to have. And the Graal virtual machine basically makes use of the optimizations that have been made over the years in the Java virtual machine to make this possible for dynamic languages as well. And we'll see in the slides how this is done. The other interesting thing about the Graal project is that it's written purely in Java. So basically, the Graal virtual machine provides a way to basically make use of the optimizations of the JVM, but it's written entirely in Java, and it provides also a Java API for language interpreters to develop their own languages. This API provided by the Graal VM is called Truffle, or the Truffle API. So the Graal JIT compiler essentially generates machine code from an optimized abstract syntax tree. So basically it uses a different form of representation of the source code, not bytecode, but an abstract syntax tree that it uses to optimize calls and to generate machine code that's executed from the Java virtual machine. However, apart from that, the Graal virtual machine also supports the execution of bytecode. So it has bytecode interpreter that allows you to execute bytecode in the same way as the JVM does. But on the other hand, it works on this abstract syntax tree data structure in order to execute and to generate machine code. In that regard, the Graal virtual machine supports several types of just-in-time compilers. The first one is the server or server no Graal. This means that when you run with this option, basically, the Graal JIT compiler is not used. So apart from a virtual machine, Graal provides also a few just-in-time compilers that work on this abstract syntax tree data structure. So the first one is VM server no Graal, which means that you run the Graal virtual machine, but you use the standard server compiler for the JVM. The other option is the VM server, which uses the JVM server compiler. However, at some points in time, the Graal VM may decide to use the Graal compiler to optimize some of the calls. And this is this option. The third one is the Graal option. So you can run the Graal virtual machine by saying that all of the time you want to use the optimizations that are provided by the Graal compiler, and it will use the Graal compiler to generate machine code. You also have the VM client no Graal and VM client, which you already understand what they do. So basically the VM client no Graal option uses the client JVM compiler without Graal, and the VM client option uses the client compiler along with the Graal compiler when the JVM decides to compile using Graal. Also, apart from Graal, we have the Truffle API, which is basically the layer that language interpreters use to develop their language in Graal. It's basically a very simple API that provides some annotations that you can use in order to build your abstract syntax tree that represents the structure of your language. The Truffle API is a Java API. It provides abstract syntax tree representation of the source code. However, that abstract syntax tree that is built from the Truffle API is not the same as the Graal abstract syntax tree. So the language developer basically provides different structures for his abstract syntax tree. Then this abstract syntax tree is converted into a Graal abstract syntax tree, out of which machine code is generated. We'll look into this process into a bit more details. So the Truffle API essentially is declarative. It uses Java annotations basically to generate the abstract syntax tree. And the abstract syntax tree that's generated by Truffle is a mixture of a control flow and data flow graph. This means that it operates not only on the structure of your language, but also on the input that's being executed. And basically the Graal virtual machine tries to make some assumptions on what is the type of input that you provide to your application. Essential feature of the Truffle API basically is to specify so-called no specializations, which means that for different type of input, such as for example string, boolean, or any other type, you can specify different execution logic for your program. So here is basically the process of how you would implement a language in Truffle. You write basically your language using the Truffle API, and you need to write your own parser in order to parse the input of the language. When you build a Truffle structure for your language, it's compiled using the JavaC compiler, since it's a Java source code. Then on top of that JavaC compiler, an annotation processor is used that processes the annotation that you have used for your language. And out of that, additional source code is generated. After this code is generated, you have the compiled form of your language interpreter. And here is the general architecture of the Graal VM. On top of it, you have different language implementations. You have implementation of JavaScript, Ruby, R, your own language, whatever you can think of. And it's written basically using the Truffle API, which is basically a Java API. On top of the Graal VM, you may run, as usual, Java applications or any other applications that execute under the JVM and are not written using the Truffle API. The Graal virtual machine essentially is written in Java. However, it provides the so-called Graal hotspot adapter that allows it to execute machine code using the hotspot virtual machine, which is written in C++. And basically, this Graal hotspot adapter is the bridge between the Graal virtual machine and the existing hotspot runtime. We have the same thing for the Maxim VM. Maxim VM, for your additional knowledge, this is a so-called meta-circular virtual machine, which is a virtual machine written in the Java programming language. And it's also a research project that's being developed by the same team that develops Graal. And also for Maxim VM, we have a bridge that allows us to execute machine code in the Maxim runtime. So this is the general architecture of the Graal virtual machine. Now, let's see, using the same picture, how basically a JavaScript program is executed using Graal. So first of all, you write your JavaScript file. you create a parser for it, and you run it. You basically have an implementation of the Truffle API for your JavaScript interpreter. It parses basically the JavaScript file and converts it to a Truffle abstract syntax tree, which is a Java application. When this is done, the JavaScript file the abstract syntax tree that represents your application is converted by the Graal virtual machine to additional abstract syntax tree, which is more convenient for optimizations and for generation of machine code. And this is done by the Graal virtual machine. After this happens, the Graal virtual machine basically has an AST interpreter along with the bytecode interpreters that it already has. And it uses a number of optimizations such as AST lowering that allows it to generate machine code. So basically at some points in time, the Graal VM may either execute parts of your abstract syntax tree and interpret it, or it may generate machine code from it and use the Hotspot VM adapter to execute it. So when parts basically of your application is compiled to machine code by the Graal compiler, that code is transferred to Hotspot for further execution. However, at some points in time, if by some reason the Graal VM decides that this machine code is not very optimal, it may decide that it will de-optimize the source code from the Hotspot runtime back to the Graal virtual machine. An example of this is if your application throws an exception. If your application throws an exception, then Graal VM decides that it is more convenient for the Graal runtime to handle all of the display of the stack trace, the handling of the exception, rather here at the Hotspot runtime. So this is one case when the optimization is needed. Another case is that your interpreter may have some routines that tell basically that some particular part of the source code should not be optimized, meaning that it should execute only in the Graal virtual machine as interpreted code, rather than being compiled to Hotspot, to machine code and executed by Hotspot. So this is the case when we may have some type of de-optimization. And Graal also supplies different types of optimizations that are executed on the abstract syntax tree and allows it to optimize your running source code. Some of them are method inlining that allows you to basically take some method invocations and place the source code of that method directly at the execution point. It has also partial escape analysis when it tries to determine if some variables are encapsulated in some particular scope. And in that case, it can execute and create them on the stack rather than on the heap. We also have inline caching, and this is basically functionality that allows the Graal compiler to store some particular execution points with particular input when it executes a method. For example, imagine that you have an application, a JavaScript that executes some method and passes every time some integer. So basically, when you execute the first time this method and pass it some integer, the Graal VM basically remembers and caches that you have an integer as an input to that method. And every time that you execute that method again from the same execution point, it basically tries to take reference directly from the cache rather than trying to find much for this method. So basically, this is inline caching. It's an optimization technique that allows you to optimize the calls to various methods based on the input. We also have constant folding. We also have various types of arithmetic optimizations and so on and so forth. Currently, the Graal virtual machine supports a few languages out of the box. There are implementations for JavaScript, which is Graal.js. We have R, which is named FastR under the Graal ecosystem. We also have implementation for Ruby. And there are also currently some experimental interpreters for C, Python, Smalltalk, LLVM, intermediate representation, and so on. Some of them you can find on GitHub. So basically, if you want to develop your own language, you can use them as references. The JavaScript one is still not open sourced. It's being developed in-house by Oracle Labs. However, if you want to start with your own language implementation, there is the so-called simple language project, which provides a very good starting point with a lot of documentation that you can use basically to create your own language, if you like. And basically, the simple language is really a showcase of how does the Truffle API work in terms of the Graal virtual machine. So if you want, the simple language works as usual. It parses some source file of the simple language. It provides some example parser for parsing the source file. Then it provides Truffle structure in the source code, and that's executed by the Graal virtual machine in the usual way as you would write a language that implements the Truffle API. So now let's see, after all, how we can build the Graal virtual machine and how we can use it. Currently, basically, the Graal virtual machine is provided as a standalone project that you can download from GitHub, build yourself, and use it. There are also some binary distributions for Windows and Linux that you can try out directly without building the Graal VM manually. Also, the Graal VM interoperates with the so-called Java language compiler interface. The JVM compiler interface, which is developed under Java Enhancement Proposal 243, is basically an API that allows compilers that are written for various languages that run in the Java virtual machine to use some APIs provided by the Hotspot runtime for various optimizations. And one of the ideas of the Graal project is to be able to be shipped as part of the JDK, and for that reason, it needs to use some standard API for communicating with the Hotspot JVM. Currently, the Graal project has some modifications of the Hotspot runtime in order to provide this communication between the Graal virtual machine and the Hotspot runtime. However, they also support the compiler interface so that you can use and run the Graal virtual machine on top of an existing Java virtual machine, which is not possible as of JDK 8. So this interface will be part of JDK 9. So in that regard, we have two modes of operation. You can have a standalone Graal virtual machine that uses a modified version of Hotspot, or you can use a Graal VM that runs on top of an existing JDK that provides the Java compiler interface. Yeah, as we mentioned, early access builds are available for Graal, so you can download it, you can try it out. And you can also build it yourself. There is a very convenient tool that you can use for that purpose. And that tool is called MX. It's provided as a separate project, and this is basically how you can use it. You need to clone the MX repository. You need possibly to export the MX tool so you can use it from anywhere. Then if you want to build a version of Graal, you go to the Graal core project and execute MX. Then specify what type of virtual machine you want to build. It's Graal, server, client, and so on and so forth. And you say build. This will basically build a Graal version of the JVM. And if you want to execute that JVM, you say MX VM. And basically that's it. And the MX tool basically is a Python tool which is very convenient, and it provides a number of things that are currently lacking from the build process of the JDK itself. Some of them are, for example, the ability to update source code and to run unit tests and benchmarks on your Graal interpreters. It also allows you to build sub-projects separately, so you can build C++ sources that are provided by the Graal VM separately from Java sources. It allows you to run some VM tools that are provided by the JDK, but you cannot execute directly. Some of them are the Ideal Graph Visualizer, or IGV, which is basically a tool that allows you to visualize the intermediate representation of Graal, or the abstract syntax tree. So this tool is very useful not only for the developers of the Graal VM, but also for language interpreters, so that they can see how is their language being represented internally by the Graal VM. You also have a number of other tools that you can use for the purpose. And also the MX tool can be used to generate ID-specific files for Eclipse in the IntelliJ that you can use to start developing your own language interpreter. Okay, so let's see some things in action. I have a virtual machine which which has already the Graal projects. So first of all, if you go to GitHub, you can see what projects do you have in the Graal group of projects. We have the MX tool that you can use to build Graal. You have Graal core, which is basically the Graal compiler and the Truffle API that you can use. Here are the sample implementations of some of the languages. We have implementation for Sulong, which allows you to execute LLVM code in Graal. We have FastR, which is the implementation of the R programming language for Graal. We have JRuby, and so on and so forth. Now, if you want basically to try out Graal, first you need to get the Graal virtual machine and the MX tool. Can you see actually or not really that well? Let me try to increase a bit. Okay, is it better now? Yeah. Okay, so the first thing basically is I have here downloaded the MX repository. So the MX tool basically, if you run it, you first need to add it to your path. So if you run MX, you can see what options do you have. It's really very rich. You have a number of options that you can use, number of commands. Some are, for example, allow you to basically find all classes that match something, or to build the project, or to generate some ID-specific files using, for example, the ID init command or IntelliJ JUnit to generate IntelliJ project configuration. So in fact, it's a very rich tool that you can use. Now, if you want basically to try out something, you can download the binaries of Graal VM, and I have Graal VM here. But before that, let's see, for example, a very simple JavaScript file. I have a JavaScript file here that is just some simple JavaScript loop that prints some number. And basically, finally, I print out the result. So this basically is a sum of some numbers that are passed to the JavaScript function. And now I want to execute that file from the JavaScript interpreter that's provided by the Graal VM. For that reason, the Graal VM provides a JavaScript runner, which is under Graal VM bin.js. And if I use that runner, I can simply execute the JavaScript file in a very simple and usual manner, nothing specific. As you can see, here the numbers are printed, and finally I have the result. The first time you can run your application, it might be a bit slow, but with any subsequent run, there might be already some optimizations that have been done beforehand, so it might execute faster and faster by the Graal VM. Now let's see something more interesting. As I mentioned, you have the so-called simple language, which is basically used to demonstrate some concepts of Graal. Let's see, for example, some simple language files. Let's see, for example, the example loop SL file, which is basically a very simple application. It has a syntax which is very similar to JavaScript, but not the same one. So in this particular case, I have some function which also calculates the sum of some numbers and finally returns that sum. I also have a main method, which is my entry point, or the entry point for my application, which is something that I don't have in JavaScript, for example. And it does some things, basically. It calculates what's the time necessary to execute the test function with some initial value that has been supplied. And finally, basically, it prints the result. So basically, this simple language can be executed by the simple language interpreter. For that reason, there is a run tool provided by the simple language project, which does nothing more than providing basically execution of the SL file, which basically runs the simple language interpreter. Let's see how this file looks like. Bin cell. Oops. As you can see, there is nothing specific here. We just basically take a build of the simple language, which we may build with Maven, Gradle, or any tool you would like. And we execute the program as an argument to that application that we have supplied. So I can run this program using this run utility. I can say run example loop SL. And it starts basically running the application. At each iteration, it specifies what's the execution time of the method I've executed. As you can see, the first time it executes quite slowly, for about 1.5 seconds, but with each subsequent execution, it runs almost linearly. The reason for this is basically that the Graal VM has managed to do some optimizations on that method and to make it much faster, maybe to do some inlining and so on. The next interesting thing that I can show is basically what's the internal structure of that application. So if we basically want to see how does the Graal VM represent our application, we can use the ideal graph visualizer tool for that purpose. In order to run the ideal graph visualizer, you have to go to the Graal repository, which is Graal core. And you have to execute mxigv. I'll run this tool in the background. Once basically the tool is run, I can execute my application again by specifying a few JVM parameters that allow my application to dump some useful information that's used by the tool to generate the intermediate representation. Now if I go back to the sample language, and now I basically want to execute again this example loop application, but also to dump information to the ideal graph visualizer in order to be able to visualize the abstract syntax tree for my application. Let me see if the ideal graph visualizer is already executed. Okay, so basically in order to be able to execute the ideal graph visualizer, latest versions of the Graal VM require me to supply also version of the JDK that has the Java compiler interface supplied. So for that reason, I cannot simply say mxigv, but I also need to supply the JVM. So for that reason, I have basically small cheat sheet here. So what this does basically, it supplies a Java version that has the Java compiler interface already. And using that version, I want to execute the ideal graph visualizer tool. But I need to execute it from the Graal core project. So basically, the ideal graph visualizer is a tool provided by the JDK. It's already part of the JDK, but it's not used that much by developers. It's really useful to visualize the intermediate representation, not only for the Graal VM, but also for the existing client and server compilers, since they already also use some intermediate form of an abstract syntax tree to generate machine code. So now that I've executed the ideal graph visualizer, I would like to go back to the simple language project, and I would say run with some magical options, -G, -J, dump, and I'll supply my application, which is example loop. What this does basically, it executes the application and dumps some information to the ideal graph visualizer. So if I go back to the tool here, I can see that I have some information supplied to the visualizer. And I can also using that information, I can basically visualize the representation of my application. As you can see, that representation is an abstract syntax tree, which has a root node, which basically represents the main method of my application. Can you see it better? As you can see here, you have a number of different types of nodes. You have SL while, SL block. These are basically classes that are implemented by the simple language interpreter. SL stands for simple language. And I have a number of constructs that represent the structure of my language. SL while represents the while loop of the application. If we basically go back to the example and see the structure, we have a main method which is represented by SL root. So SL root basically is the main entry point, which basically is some function represented by SL function body. And that function has a number of things that it executes. So the first thing actually is that it writes two variables, iteration and value. And here is we have SL write local variable node gen. We have two such nodes, which basically represent the assignment of variables. Then we have a while loop, which is represented by SL while node. And finally, we return, by default, we return void. So we have some SL return node, which represents the return from our block. And from these nodes, we descend further to the other instructions in our application. So basically, in that way, you can inspect what's the intermediate representation that Graal supplies to your application. Okay, any questions so far about Graal? Okay.
I have one.
Yep.
You said that there are interpreters for JavaScript,
Mm-hmm.
R, etc. So is it possible that someone can say, okay, I can write faster interpreter for JavaScript? Can he plug his own interpreter for JavaScript, or does he have to use this already supplied?
Well, there are a couple of options. You can write your own interpreter for JavaScript completely independent from the one supplied by the Graal team, and it will still be valid. It will have some more work to manage to get all of the parsing and the interpretation of all of the JavaScript language structure. But in general, if you think that you can extend the support for JavaScript in the current Graal VM interpreter, you can use the current JavaScript. You cannot, because it's currently not open sourced yet. But in practice, when they open source it, it should happen in a few months' time, I guess. You can also review it and supply some improvements, bug fixes, and so on. But at this point, for JavaScript in particular, it's not in GitHub, so you cannot view the source code directly.
Okay. And what? Sorry, just one more.
Yeah.
What is the relation between Graal and existing support for executing JavaScript in Java? I think it was
Mhm.
Rhino or
Yeah.
before now.
Well, it's an interesting question because these are two completely independent things. One is basically JavaScript implementation running in Hotspot. It has absolutely nothing to do with Graal. And the JavaScript or the Graal JS project is another project which is a showcase of a JavaScript interpreter running under the Graal VM. So basically, the developers of the Graal virtual machine try to promote the idea that every JVM language should have an implementation for Graal. It should supply this Truffle API implementation for an interpreter, and it should implement its language like this. But this is currently not how it's been done, for example, with Rhino or with Kotlin or any other type of JVM language which has just its own interpreter. Yeah. Any other questions?
If we are running JavaScript, is there a way we can to create multiple JavaScript files and say this is dependent file and I want to run this one?
Well, it depends. So in this particular case, we executed just one JavaScript file. If you use some libraries such as require.js and so on to basically bind the different types of JavaScript files, in practice it should be possible if you supply all of the files somehow to the Graal VM, but I'm not really sure on this. It should be possible, but I have to check it. Yeah, I'm really not sure, but it should be possible.
One more question. Can this be used, for example, just to check if JavaScript file is syntactically correct?
Yeah, absolutely. If basically you cannot parse the JavaScript file, you can supply, it's very good because the Graal VM provides some very useful utilities for you to log some errors or error messages during the actual process of interpretation of your JavaScript. So you can supply your own custom logic to log some specific error messages that the user can see. For example, if something is wrong during the parsing of because basically the parsing process is not provided by Graal. You rewrite the parser for the JavaScript file yourself. However, when you have the parser, you have to, using the parsed information, you have to create this Truffle API structure that is used by the Graal VM to execute your applications, written, for example, in JavaScript. So basically, during the parsing phase, you can supply whatever you like to the user, such as some information for some parsing errors and so on. And during the interpretation phase, the runtime execution of your application, you can also specify some routines in the Truffle API that allows you to give some information to the users, such as some useful log information and so on. So it's basically customizable. Yeah.
Is there some kind of debugging? Because when you run that JavaScript or whatever code, is there some kind of?
Well, since basically it's JavaScript, so you Java, your interpreter is written in Java. You can use the standard Java debugger to debug your interpreters.
No interpreter, but that code that is run. On Graal VM. For example, JavaScript code or Ruby or R, whatever. So it's parsed. That tree, syntax tree is created and you optimize and then execute it. And does it have some connection with the lines of code as you debug some hidden? Is there some kind of support?
This is really actually a very good question. So basically, the Graal team provides some routines when you implement your interpreter that you can use basically to plug in a debugger. So basically, it is possible to debug to supply debugging routines for your languages, but I don't have a particular demo for that. But it's possible, yeah. Okay, so now let's see shortly some performance benchmarks. And basically, some of you may think, well, there is a Graal project, but why should I not implement my own interpreter that runs in the JVM? Why should I use the Truffle API? And the reason really is performance. You want to make use really of the performance optimizations that have been done over the years and have been improved and improved. And according to some standard benchmarks for the JVM, basically, the Graal compiler positions somewhere between the client and the server JVM compiler. The client compiler, as you know, basically provides faster startup time, but slower optimizations during execution. And the server JVM compiler provides more optimizations during the startup of your application and faster execution of your application during execution. And the Graal compiler positions somewhere in between the two. Typically, in general, the Truffle interpreters provide much better performance for some of the dynamic languages that are currently supported by Graal than if you write those interpreters directly using the JVM utilities. And here are some short statistics. For example, for Graal.js, in some cases, we have even some performance improvements over V8, which is considered currently the fastest JavaScript runtime at present. In worst cases, we have around 2.6 slower execution compared to V8, which is really not that bad. For Ruby, the improvements are between 1.5, 4.5 times compared to JRuby. But in some cases, really, we have 14 times better performance for some specific cases. For fast R, since R is a language that's not been targeted for performance, we have in some cases up to 94 times of performance improvement. And in the general case, it's between 2 and 39 times of improvement. Basically, the Graal team is trying to make this even better. So this picture with time is supposed to look better and better since they try basically to optimize more and more on the cases where performance is really degrading over some other implementations. And to conclude, basically some future directions for the development of the Graal project. As we saw, basically Graal provides actually an extensible framework for research and experimentation with not only the implementation of other language interpreters, but also for implementing various types of compiler optimizations. If you decide to research and try to experiment with the compiler optimization, you can use the Graal VM basically to try out and use your optimizations based on existing language implementations. So in that regard, the team continues to improve and to supply more optimizations to the Graal virtual machine. Graal also provides a framework for creating language interpreters, as we saw. So the goal of the team is to continue to improve the performance of the existing implementations that we saw, but also to supply implementations for other types of languages that are executing on the JVM. Currently, the team, as we already said, tries to promote the idea that every language interpreter should try to create a Truffle API implementation for his language and to compare that with the implementation that this language already has for the JVM in order to see if that's better in terms of performance. And last but not least, the Graal VM also provides a pluggable framework for experimenting with different types of CPU architectures and operating systems that are supported by the Graal VM. So in that direction, the team has already a goal to provide support for more types of architectures and operating systems that would allow us to run the Graal VM. And basically that's it. To conclude, any questions? Yep.
You said that in case of exception,
Mm-hmm.
virtual machine will decide that already just code which is already compiled to the machine code will be returned back.
Yes, de-optimized.
One question, is that only for the Graal or also for the Java hotspot machine itself?
For the hotspot machine, basically, it's pretty much the same. So basically, when you have some exception that is thrown by the code, basically control is returned to the interpreter so that it can process everything around the exception. But it's working differently. It's not similar to this, but the idea is the same, basically, that control is transferred to the interpreter.
I'm asking that because that means if we are creating code which relies on exception,
Mm-hmm.
part of the code in standard Java will never, if there is exception, it will be returned to bytecode.
Yes, yeah. But it's very optimized. So it sounds like this is a very slow procedure to transfer control back from the runtime to the bytecode interpreter. But in practice, it's not really that slow. So they've optimized really this. So basically, at the point where an exception is thrown, you just return directly the execution to the interpreter. And you've already preserved the bytecode instructions that, or the part of the AST that corresponds to that particular machine code. So you just return control back to the interpreter. Okay, yeah.
Is it possible to add any additional adapter other than to hotspot?
Yeah, absolutely.
Yeah.
Absolutely, but in order to add that adapter, you have to be one problem is that these adapters are not well implemented. So if you want to supply your own adapter, you have to go and see how is basically the one for Hotspot implemented or the one for the Maxim VM implemented. There is no currently standard documentation in place that specifies how is basically the Hotspot adapter implemented and how is the Maxim adapter implemented. It's inside the source code. So you can get the Graal core project and go and see how is it implemented.
Okay, thank you.
Yeah, welcome. Okay. If no more questions, then thank you for attending the talk. I hope it was useful and interesting to everyone. And yeah, thank you.